Hello everyone, welcome to the channel. I hope you all are doing great. So we were discussing about our previous year questions of the UPSC Geoscientist exam, and in that we have started with the analytical chemistry portion. The first part of it we have already discussed, where some of the questions we discussed of this particular topic. Now in this video we are gonna cover the remaining topics for it. So this was the syllabus that I introduced to you, and these were some of the questions that we did in the last class. Now the remaining questions, as I said, we will be completing in this class. So next one we have is, just a second, these all we discussed. Now this is the question that we are to discuss. Before that, this is the one. So this I gave you that you can firstly try it yourself and then look to the answers. So I hope you would have tried this one. Now we are gonna see the solution for this. Okay, so it says what will be the approximate concentration of H positive in a solution having a pH of 5.5. Very easy question I gave. So it was pH, we know it is nothing but the negative log of the H positive. Right? pH value it is given to us as 5.5. So this is negative log of H positive. So from here you just have to find this the H positive concentration, which is NT log of minus of 5.5. So I told how you can find the NT log without calculator if you have to do this. So for that what you will be doing is you will be going one number ahead of it. So here you are having this 5.5. So next to 5 is 6. So we will be adding 6 and we will be subtracting 6. So it is NT log of minus of 5.5 plus 6 and minus 6. Right? And minus of 6. So this term, that is plus 6 and minus of 5.5, this is gonna give us the value of zero point 0.5, right? So it is gonna be NT log of zero point 0.5 and this is minus 6. So that you will be writing it as NT log of minus 6 you are having. So this will go in the 10 raised to the power of it. So it will become 10 raised to the power of minus of 6, and here anti-log of zero point 0.5. So I told you can remember from 1 to 10 the logarithmic values. So log 1 you have it is 0. Log 2 it is 0.3010. Log 2 it is this one. Next is point log 3, if you see it is 0.477, and next the log 4, which is nothing but the 2 times of the log 2, which will come out to be as 0.6020. Now you see we have is the value of the anti-log, that is of the zero point 0.5 we are having, right? So zero point 0.5 logarithmic value, it is gonna lie in between log 3 and log 4. So that means our answer will be in between these two only. That will, if when it suppose it is approximately 3.2 into 10 raised to the power of minus of 6, from the options you can see this value it was given, that is why I have taken it this one only. Right, so this is how without calculator we can solve this. So if you will be taking the logarithmic terms of it, pH value you will be getting it as 5.5 only. So this is how you have to solve this. Okay. So this is the hydrogen ion concentration. So the answer it becomes the option A in this case. Okay. Now moving upon to our next question, we have is this one. So the next question is this. I gave it to you to try it yourself. I hope you would have tried this one. Now solution to this, it says 100 ml of zero point 0.1 molar ethanolic acid. Ethanolic acid, it means the acetic acid or ethanoic acid. It is also called as ethanolic acid. Okay, so this is my acetic acid. Solution, it is neutralized with zero point 0.1 molar sodium hydroxide. This you know it is your NaOH, right? The pH of the solution at the equivalence point, what the pH value you will be getting. So here we are having is the acetic acid and this is treated with the NaOH. This is gonna give us the formation of sodium acetate, O negative, and Na positive, and along with this the water it will be present. Now a term is given to us over here is that is at equivalence point. What is meant by the equivalence point? At equivalence point, the acetic acid that you are having, it is completely reacted with the NaOH, right? So what it basically we are doing is, in the conical flask you were having the acetic acid like this, and from the above you were adding the NaOH, right? So all the acetic acid that you are having in this beaker, at the equivalence point, all of it will be reacting with the NaOH, and after the equivalence point, when you are going to towards the end point, you will be adding is the further NaOH addition it will be done to this in the conical flask, right? So at the at equivalence point, all the acetic acid, all the acetic acid is completely reacted with the NaOH, reacted with NaOH, right? So that means the sodium acetate which is getting being formed in this case, it is dependent upon the acetic acid concentration, because that is your limiting reagent. Here, since equal amount of it is given, that is 100 ml of 0.1 normal. So this is what the sodium acetate would have been also formed over here. So that means its concentration will be 0.1 molar only, right? Now, this sodium acetate that we are having, this we will be having at the equivalence point. This on treatment with the NaOH and the water, that is the aqueous medium that we are providing, because the water will be present, it can undergo the hydrolysis and will form the acetic acid, and along with this the NaOH will be formed, which means the resulting solution it is gonna be basic in the nature, because NaOH is getting being formed, which is your strong base you are having, or you can say it in the other way also. The NaOH addition we are doing in the beaker after the equivalence point. So after that also this OH negative ions will be present in my solution. So OH negative is formed in my solution, is formed in the solution. So that means we will be dealing it with the basic medium. So for that we need Kb value. Here you are given is the pKa of the acid it is given, but we need is the Kb value for this. So one formula we know that Kw, which is ionic product of water, it is equal to the product of Ka and the Kb. So Kb value it will be equal to the Kw upon the Ka of it. So Kw we know at the room temperature its value is 10 raised to the power of minus of 14, and the Ka value it will be 10 raised to the power of minus of 4.6. How we have done this? pKa is 4.76 we are having. So pK is negative log of Ka, which is equal to the 4.76 only. So Ka value is 10 raised to the power of minus of 4.76. So it is log to the base 10 only it is taken. That is why we can write this directly. In the previous case also, when we were solving this anti-logarithmic, that was taken 10 raised to the power. That is why minus 6 it was written as 10 raised to the power of minus of 6. Okay. So Kb value you can find it from here, which is gonna be equal to 10 raised to the power of minus of 9.24. Right? Now, for the Kb value, you will be having Kb can be written as the product concentration, which is this acetic acid, into the water. This not the water, this OH negative ions which are getting being formed. This equilibrium we are using it now. This one. Okay. So this is the one that is getting being formed. So we are having the acetic acid, and along with that the OH negative is getting being formed, and in the denominator it is gonna be this acetate ion over here. right? So these concentration of the acetic acid and OH negative, it is not given, so we can consider them to be X and X only. And here is this acetate ion concentration, which is equal to the X square upon the 0.1 minus of the X, because acetate ion already you have formed its concentration to be zero point 0.1. Some of it might be reacting with the water, that is giving you the X and X formation of this acetic acid and OH negative. So some amount of this, suppose this is initially zero point 0.1 you are having, this one formed will be negligible. After some span of time, some X amount of it will be reacting and forming the X and the X amount of these two. That is what we are writing it over here. So this you can say that negligible amount of this acetate has undergone the hydrolysis. So we can write it as X square, and zero point 0.1 minus of the X we can take approximately equal to the zero point 0.1. Okay. So equate these two with the Kb value now. So Kb value we got it as 10 raised to the power of minus of 9.24, which is equal to the x square upon the zero point 0.1. So x square, it is gonna be equal to 0.1 into 10 raised to the power of minus of 9.24. Alright, so from here this x value, when you will be solving, you will be getting the value as 10 raised to the power of minus of 5.12. Right, so this is nothing but the concentration of the OH negative you are having. Right, so from here we can find the value of the POH, which is nothing but the negative log of OH negative, that will be equal to negative log of 10 raised to the power of minus of 5.12. That value comes out to be as 5.12. We need to find as the pH value. So pH will be equal to 14 minus of this POH value, which is 14 minus of 5.12. That will be getting it as 8.8. So this is how this question was to be solved, because some at the equivalence point term is introduced, and after that what processes are gonna take place, all this has to be taken into the consideration. So the correct answer, it will be 8 point, what we got it, 8.83 we have got it, so 8.8 approximately, so close to the A option only, that is 8.73 it is given. So this is the answer we will be having that. Okay, now moving upon to our next question we have is this one. So very simple question, just the ratios, this definition of the specific gravity is being asked. Specific gravity, it is nothing, specific gravity, it is defined as the ratios of the density of the solution to the density of the water. It is density of the solution to the density of the water. Density of water. So this ratio we call it as the specific gravity, and density we know we can write it as mass upon the volume. So it is mass of the solution upon the volume of the solution upon density of water. We can just write it as mass of the water upon the volume of the solution. Volume of the solution. Volume of the water here. It will be volume of the water. If you have the volume of solution and volume of water to be equal, let volume of the solution is equal to the volume of the water. So at that point the specific gravity, yes, I am denoting it with this specific gravity, that will be equal to the ratio of the mass of the solution to the mass of the water, to the mass of the water. So this is gonna be the definition of it. From the options you see, it is ratio of the mass of the solution to that of the mass of the equal volume of the water. So this statement is your correct one. Right? Next definition, it says ratios of the two molarities, no. Ratios of the normalities of two solution, no. Ratios of the volumes of the two solution, no. It is densities ratio generally we take it, but if equal volume you are having, it will be the ratios of the two masses. Okay. Next one is this. It says a solution of the oxalic acid needed to be heated up to 60 degrees centigrade before titrating with the potassium permanganate solution. Okay. Which of the following is not a reason for this? So whenever you are performing the oxalic acid, I hope you remember the experiment. It's generally performed in the lab. That in the conical flask, if you are taking the oxalic acid, this is the oxalic acid. This you have to heat it firstly. The reason for the heating is that it's these are some of the reasons I are given. That is only the one. One of them it is not there, that you can get from here. Okay, some heating process has to be done. So that rate of reaction it is increasing. You can remove the carbon dioxide from the solution. So these are some of the reasons. Okay, so first one it says it helps to remove the dissolved carbon dioxide from the solution. This statement is true. Next one it says it helps in increasing the rate of reaction. This statement is also true because by heating the molecules will start moving at a faster rate. So their rate of the reaction it is gonna increase only. Next is high temperature. It decomposes this complex if formed during the titration. This is also your true statement. Some complex formation if it has taken place, that also will be destroyed by heating. Next, it says oxalic acid it precipitates at room temperature. This is incorrect one. You might have seen that it always remains into the liquid solutions and it never undergoes the precipitates. So heating is not done to remove that precipitates. It never undergoes that. Okay. So this is not the reason. Oxalic acid never undergoes precipitation. Oxalic acid it does not precipitates precipitates at the room temperature. Its PPT are never formed, right? So the heating is done to remove these to do these processes and not to remove the PPTs. Okay. Next one is this. It says during the ideometric titration of the copper sulfate solution with the sodium thiosulfate solution, what the student does is a student uses a starch solution as the indicator. So for the ideometric titrations, starch is used as your indicator. Okay. However, this starch it has a specific color which is your bluish black color. That is gonna denote the end point of your reaction. However, the blue-black color obtained with the indicator it did not appear. So indicator was added, but the endpoint we are not achieving in this case, even after adding the required amount of sodium thiosulfate from the burette that is at the endpoint. So how do we perform it? Here you have is this conical flask you are having, and in this you are having the copper sulfate solution, and along with this the iodine is added. It is iodine it is added, and from the burette we add is the sodium thiosulfate Na2S2O3. Now along with this a indicator has to be added, that is the starch indicator. It is the starch as the indicator. But the point of addition of this starch is very, very important. The possibility is if you are adding the starch in the beginning of the reaction only. At that point, you won't be getting the end point because this iodine which is present, it will be not reduced by this sodium thiosulfate. So addition of this starch has to be done near the end point. Suppose some of the reaction you have done it already. After some time, if you might get an idea that the end point is about to reach over here. At that point, near that the starch has to be added. Okay. So in the hydrometric titration, starch which is used as the indicators, it is gonna form the bluish black complex with the iodine, but it is added near the end point when most of the iodine it is reduced by this sodium thiosulfate. So what the student made the mistake is that he added the starch solution in the beginning of the titrometric performing the titrations. Okay. So starch solution was added in the beginning of the titration. That is why we did not got this bluish black color. Okay, so let me just note this point in this ideometric nitrate, titrations, starch is used as indicator that forms complex that forms the complex with the iodine with the iodine. So due to that this bluish black color is obtained, but it has to be added it has to be added near the end point near the end point near the end point where most of the iodine most of the iodine has reacted with the sodium thiosulfate, has reacted with the Na2S2O3. So in the beginning only if we are adding this starch, so what is this is gonna do is sodium thiosulfate will react with the iodine, and most of it will be remaining the unreacted only, and starch won't be forming the complex with the iodine. Okay, because iodine it is not reduced by this sodium thiosulfate, so that is why it has to be added near the end point. So this is gonna be the correct answer in this case. Okay, now the next one we have is this question. It says how many milliliters of 0.25 molar solution of sulfuric acid will react with 10 ml of the 0.25 molar solution of the NaOH. So treatment is of the H2SO4 with the NaOH. So it is gonna give you Na2SO4, and along with that the water will be formed. Here a factor of 2 it has to be included. At the end point, at the equivalence point, it's better to say at the equivalence point, equal amount of this would have been reacted. That means N1V1 will be equal to the N2V2, that is N1V1, that is number of gram equivalents of the H2SO4 will be equal to the number of gram equivalents of my NaOH, right? So for the sulfuric acid, its uh, molarity, or the molarity it is given. From the molarity you can derive the normality. Normality is nothing but the molarity into the valency, or we can call it as the N factor. I told in the last class also that for the acids this N factor is equal to the, for the acids, N factor is equal to the basicity. That is number of the replaceable hydrogen ions that particular acid that is having. So in the H2SO4, you have two of this replaceable hydrogen ions. So the N factor for this case it is equal to the 2. So normality for the sulfuric acid, it is gonna be 0.25 molar into the N factor, which is 2, into the volume that we have to find it out. This is equal to N2V2. For the NaOH, we have the molarity as 0.25 molar. The N factor for it is equal to the 1. For the bases, the N factor is equal to their acidity, which is number of the OH negative ions they can give in the solution. Now in the NaOH, only one replaceable OH negative you are having. So N factor will be 1 in this case, and the volume it is given to us as 10 ml. So this we both equated. So with the 0.25, this 0.25 will get cancelled out. Volume we are getting it as 10 by 2, which is equal to the 5 ml. Okay, so this is gonna be the answer, that is the option C. Okay, moving upon to the next one. This statement based it is that which one of the following statements is the correct? So water is a strong electrolyte. Is water a strong electrolyte? No. Water is a weak electrolyte. Only the partial dissociation it shows. Next is the value of the ionic product of water. It varies with the temperature. This statement is the true one. This Kw value that you have, it is temperature dependent. It is temperature dependent. So that is why whenever I am using this term that Kw, it is 10 raised to the power of minus of 14. This is at room temperature, that is at 25 degrees centigrade. As you increase the temperature, the dissociation of the water it increases. So Kw is nothing but the constant product of the concentration of H positive and the OH negative. So when you are increasing the temperature, this dissociation of water it is gonna increase. How we have got this Kw? Water it dissociates like this, H positive plus the OH negative. If you write the dissociation constant of it, it is H positive into the OH negative concentration upon the water concentration. If you take this water into the Ka side, Ka into the water, this will be equal to the H positive into the OH negative ions, right? This Ka into the water is nothing but your Kw, which is product of this H positive and this OH negative, right? So this is what we are having. So as you will be increasing the temperature, more amount of the water it is gonna undergo the dissociation. So Kw value it is gonna increase. That means the ionic product of water it is varying with the temperature. So this statement is the true one. Okay. And next is the concentration of H positive and OH negative ions in 10 raised to the power of minus 5 molar HCl solution are the same. It is your incorrect one. If you have 10 raised to the power of minus of 5 molar HCl, it means here the H positive concentration is 10 raised to the power of minus of 5. If the reaction has been done at the room temperature, so that you can write it as Kw we know H positive into the OH negative. That means it is 10 raised to the power of minus of 14. This will be 10 raised to the power of minus of 5 and the OH negative. So OH negative it will be 10 raised to the power of minus of 5 plus of the 5 which comes out to be as 10 raised to the power of minus of 9. So is the H positive and OH negative concentration the same? The answer is no. HCl it is there. How is that possible that OH negative will be of the same amount? It is acidic in the nature, so obviously the H positive concentration will be the higher one in this. Right? Next is the ionization constant and the ionic product of water are the same. It is incorrect. Now only I told this is Ka is the ionization constant, whereas Ka into the water is the ionic product of your water. Right? So the answer will be the option B in this case. Okay. Now moving upon to our next question we have is this one. It says the pH of a buffer solution which is containing 6 ml of the acetic acid which is zero point 0.2 molar and 4 ml of this sodium acetate which is zero point 0.2 molar will be approximately. So here again it is your acidic buffer you are having weak acid plus the salt of weak acid which is formed with treatment with the strong base, right? So for this Henderson-Hasselbalch equation we will be using, so pH, this color might not be properly visible, so pH is equal to the pKa plus of the log of salt upon the acid concentration, right? So pKa value it is given to us as 4.76 plus of the log of, now the salt we have is zero point 0.2 molar and this is volume we are having is 4 ml upon the acid we are having is 6 ml and zero point 0.2 molar, zero point 0.2 molar and the 6 ml. This is the one. So solve this. This is 2 by the 3. So 4.76 plus of the log of 2 by 3, which we can write it as log 2 minus of the log 3, right? Because log m by n is log m minus of the log of n. This will be 4.76 plus of the log of 2 minus of the log of 3. Values you might be knowing, right? So it will be 4.76 plus of 0.3010 minus of the 0.477. Just solve this and you will be getting your answer as 4.9. 4.58. Okay, so this is how the pH will be calculated. So pH is 4.58, that is in the option C, it is given to us. Okay, next one we have is this. It says, which one of the following does not represents a correct explanation for the hydrolysis constant for the equilibrium, that is A negative on treatment with the water gives us OH negative plus the HA. So we are having this A negative on treatment with the water, it is in equilibrium forming the OH negative and the HA. So if you write the dissociation constant for this, it will be OH negative into the HA upon the A negative into the water. Right, this is what we will be getting it. So generally water is just taken in the excess, so its concentration we can take it to be equal to the unity. And this Ka, if you multiply it with this K negative, you are gonna get the OH negative, or we can say the dissociation constant Ka. Instead of the unity, if I am taking this Ka into the water, this Ka it will be turning out to be the hydrolysis constant, which will be the Kh, which is product of this OH negative into the Ah upon the A negative. Okay, so this is not unity, you can say, you have taken it on this side. So this is Ka into the water. So this is KH, and this product it will be there. So here from the options, if I see, I am getting the option B. Here only the product of this OH negative and HA has been given. From the denominator, A negative has been eliminated. So this is the incorrect form for this hydrolysis constant. So D will be the correct answer in this case. Okay. Next one is this. Which of the following compounds does not form primary standard solutions? So about the primary standards and the secondary standard solutions we have learned in the last class also, where we learned about the various conditions which are required for the primary standard solutions. That is, in the lab, if you are having it with the due course of time, the chemical species whose concentration do not change with the due course of time or the temperature conditions that remains to be the same, they are called as your primary standards. Generally, the chemical species which are of the heavier weight, they are gonna be forming the primary standard solutions. Among the given options, if you see, last class also we encountered this thing, that is about the NaOH. I told NaOH is hygroscopic in the nature. It can abstract the water molecules from the surroundings. So that is why it cannot be used as my primary standard. Instead of the NaOH, I'll be using something else if I prepare this as the primary standard solution. So that is why in C2 in the labs, this NaOH solution has to be prepared. So small pellets we get in the lab, right? Some soapy touch that they possesses. So with the help of a spatula, we take that pellets and we make the solutions whenever we require the NaOH. So the correct answer will be the option B in this case. Okay. Reason being, NaOH is hygroscopic, hygroscopic in the nature. Okay. Next one we have is this. It says that while performing titration of the KMNO4 with the clear Mohr salt solution, Mohr salt solution which is your double salt you possess, that is ammonium sulfate dot ferrous sulfate dot 6 waters. Alright. This solution is titrated with the KMNO4, which is your oxidizing agent, and during the titration the iron which is present in the +2 oxidation state, it will be converted into the +3 with the help of the KMNO4. Okay. What does a student do is, a student obtained a brown precipitates in the conical flask instead of a colorless solution. So end point was the colorless solution. KMNO4 you have, this is pinkish in the color, but here after the titration, instead of the colorless solution, you are getting is a brownish color precipitates much before the end point was reached. Okay. So what would be the possible source of the error in this. So how is the reaction proceeding? Let us firstly look to that. So KMnO4, when you are treating it with the Mohr salt, which is ammonium sulfate dot ferrous sulfate dot 6 waters, this reaction it is carried out in the acidic medium. So H positive is required in this case. So what is going to happen? KMnO4 it is behaving like your oxidizing agent, and this will convert the ferrous to the ferric. Iron will be converted to the iron 3 positive. Okay, so KMnO4 it is a good oxidizing agent only when the acidic medium you are providing it. It's not that it's not gonna behave, but to perform this particular reaction, acidic medium is required. So oxidizing agent KMnO4 will be a good oxidizing agent in the acidic medium. In the acidic medium. If you do not add the acidic medium in this, so KMnO4 in that case it is converted to the MnO2. In absence of the acid, in absence of acid, the KMnO4 it gets converted to the MnO2, which is having a brownish color precipitate. So brown PPP. So instead of the Mn2 positive. So here in this case, the Mn2 positive would have been formed, which is colorless in the nature. We are getting is now MnO2, which is having a brownish color precipitate. So what the student made the mistake due to which he is getting a brown color precipitates, it is because he forgot to add the acidic medium to it. Because in that case only the colorless solution we will be obtaining it. So the reaction medium was not made acidic. C is gonna be the correct answer in this. Okay. Next is we have this. Which of the following titrations are the metal ion indicators used? That is your complexometric titrations where the indicator used was your erythrom black tea, which can form a complex with your metal ions, followed by the treatment with the EDTA. This previous complex, which was between the indicator and the metal ion, that will break, and EDTA and the metal complex it will be formed. So main thing is metal ion indicators, it is used in the complexometric titrations. Okay. Next one is this question. It says which one of the following will not make a acidic buffer solution. Now to make an acidic buffer, what we should have in the solution, that is your weak acid, it should be present. Along with this you should have the salt of weak acid with the strong base. These conditions it should be satisfied. You should have the presence of the acid and the salt. Okay. So here if I see in the first option it is given we are having 100 ml of the 0.1 normal acetic acid. Okay, and this is treated with the NaOH, which is 25 ml and zero point 0.4 normal. So here if I am doing the reaction, I will be getting acetic acid. Its amount it is given to us as 100 ml and the 0.1 normal. Right, that means how many millimoles? 10 millimoles of the 10 millimoles we are having this. Instead of the normality, you can say the molarity it is there because acetic acid, normality and molarity and factor will be the one only. So 10 millimoles or 10 milliequivalents we can say that we are having, right? So 10 milliequivalents we are having. And for the NaOH, how much amount we are having? That is given to us as 25 ml and we are having is zero point 0.4 normal. So how many milliequivalents you will be having? So here also you will be having 10 milliequivalents only. So both of them they are in the equal amount. So both of them they will be reacting, right, and forming the sodium acetate, which will be having the 10 milliequivalent considering the complete reaction it is taking place. Okay, at that point, only this sodium acetate it will be present in the reaction medium. No acetic acid it is present. That means in this case, acidic buffer it cannot be formed because only the salt is present and not the acid. You can check the other options also. Here the acetic acid it is 10 ml and zero point 0.1 normal. So how many millimoles you will be getting? Again, the 10 milli equivalents we will be having, right? And for this NaOH, it is 7.5 milli equivalents we will be getting. So after the treatment, because the reaction product, it is dependent upon the limiting reagent. Here NaOH is the limiting reagent, which means the sodium acetate which is getting being formed, this one, its amount will be 7.5 milli equivalents. The excess of the acetic acid is still present. That means it can give us the acidic buffer solution. So that means in the solution we will be having this plus the acetic acid, which is 2.5 milli equivalents. That is in the excess one we are having it. So acidic buffer it can be formed, right? Now in the next case also if you see, it is 10 ml, 100 ml of the zero point 0.1 normal, so 10 milli equivalents, and here you are having NaOH which will be zero point 0.5 milli equivalents. So again you see the acetic acid it is present in the excess, here the sodium acetate which will be forming at, you will be getting it as zero point 0.5 milli equivalents based upon the limiting reagent, and along with this some of the acetic acid which will be how many? That is zero point 0.5 only. It has only it will be 5 milli equivalents, not the zero point 0.5, 5 milli equivalents. And here the 5 equivalents of this it will be formed. I forget one decimal. Okay, so here the 5 milli equivalents of it that is still present in the excess that we are having. So again the acidic buffer it will be formed. Right? Next one, if you see, again here the 10 milli equivalents we are having, and here you are having this 2.5 milli equivalents, which means the sodium acetate which is formed. Here the complete reaction I am considering, there will be the less or more it will be there because acetic acid shows the partial dissociation, but for the while just for to see that if the acidic buffer it will be formed or not is mainly dependent upon the amount of this acid and the salt which is getting formed, right? So here the sodium acetate that will be formed depending upon the limiting reagent which is 2.5 milli equivalents of it, and the acetic acid that will be still present in the excess which is 7.5 milli equivalents we will be having it. So that means again the acidic buffer it can be formed, right? So that means it is in the option A where the acidic buffer it cannot be formed, right? Next is this one. It says which one of the following statements regarding the Oswald dilution law is not correct. So Oswald dilution law, first statement it says it is only applicable to the weak electrolytes at the equilibrium where dissociation constant is K and can be related to the degree of ionization alpha and the concentration K is equal to C alpha square into the 1 minus of alpha. This statement is the true one. So the Oswald dilution law is for the weak electrolytes only. So here if you have suppose a weak electrolyte Ha if I consider, if it is dissociating to give H positive and the A negative. Initially, if we are having C concentration of it, these formed will be negligible. Dissociation constant is suppose this degree of dissociation is suppose the alpha. So this much amount it will be decreasing. H positive formed will be C alpha. A negative formed will be also your C alpha. If you write the equilibrium constant for this is H positive concentration into the A negative concentration upon the HA concentration, that we will be getting it as C alpha into the C alpha upon the C minus of the C alpha, which is equal to the C square alpha square upon the C times the 1 minus of the alpha. So the C will get cancelled out. So it is C alpha square upon the 1 minus of the alpha. So this is how the equilibrium constant is related, and this is for your weak electrolytes only. So this statement is the true here. What slash is missing? That you can include. Next is it is only valid for the dilute solutions where the concentration of electrolyte is very low. This statement is also the true. Next, it says it's applicable to strong as well as the weak at the extreme dilution if temperature of the solution it remains to be the constant during the dilution process. This is the incorrect. Now only I told it's applicable only to the weak electrolyte and not to the strong one. So the incorrect statement will be the option C. Okay. Next is the electrolyte solution. It must behave ideally, which means that the interactions between the solvent and the solute particles it should be negligible. This statement is also your true one. Okay. So we were to find the incorrect statement. So that is the option C. Next we have is this. It says what happens to the ionic product of water at 25 degrees centigrade when it is added with the 1 ml of zero point 0.1 normal HCl followed by the 1 normal of the NaOH. So is your dissociation constant for the water, which is the ionic product of water, it is gonna change with the addition of any substance? Answer is no. Reason being the dissociation constant, that is Kw. It is function of the temperature only. It is function of the temperature only. It is not dependent upon the addition of any substances. So it says first statement is ionic product it remains to be the constant without any significant change. This is the correct statement. Next is this about the addition it is given. It won't be happening in either of the cases because it's function of the temperature. Unless and until we change the temperature, Kw it is not gonna change. Next is this one. It says which one of the following concentrations of the H positive ions indicates an acidic pH of the water at 100 degrees centigrade where the Kw value you are having is this much. So we know that Kw it is product of the H positive into the OH negative. Right? This thing we know. We also know the pH meter that you have, that is 0 to, in actual it is not the 14, it is pKw. It is 0 to pKw value that you have. So pKw it is nothing but the negative log of the Kw. Okay, so from here if we see the negative log of this Kw value, which is 5.5 into 10 raised to the power of minus of 30. So you can solve this and find the value of the pKw, which we will be getting it as 12.26. So pH scale is now instead of 0 to 14, this is up to 0 to 12.26. The midpoint of this, that is lying in between, which is gonna be 6.13. If this pH value we are having, at that point the neutral solution you will be having, because in the general we say 0 to 14 is the pH meter and in between them the 7 where the 7 pH you are having, it is the neutral solution. Below that it is gonna be the acidic medium and above that it is gonna be the basic solution we will be having. Right? Here also it's gonna be now the neutral point instead of 7 it is 6.3 and below this it is gonna be acidic and above this pH it is gonna be the basic solution. Now from the given H positive values we can find out the pH values and from that you can get an idea that whether your solution is acidic or the basic one. So the option A, if I see H positive it is 7.3 into 10 raised to the power of minus of 7. So pH value it is equal to the negative log of H positive, which is equal to the negative log of 7.3 into 10 raised to the power of minus of 7. Solving this, the pH we will be getting it as 6.13, which means the solution is neutral, right? Because in the pH meter at 6.13, the pH solution, if it is this one, the solution is my neutral. Next we have a 7.4. into 10 raised to the power of minus of 7. At this point pH value it is gonna be negative log of 7.4 into 10 raised to the power of minus of 7, which will be equal to 6.13. Again, this is the pH value is of the neutral point we are having. This is of the neutral point. Next one, if you see, it is 7.5 into 10 raised to the power of minus of 7. So in this case, pH value it is negative log of 7.5 into 10 raised to the power of minus of 7, which is we are getting is as 6.1249. So it is less than that of the neutral value. That means it is gonna fall in the acidic zone. So this concentration it represents the acidic solution we are getting it. Next in the option B also you can check it. The concentration value is 7 into 10 raised to the power of minus of 7. So pH value will be negative log of 7 into 10 raised to the power of minus of 7, which is gonna be 6.15. That is more than the neutral point, which means this is representing the basic solution. Okay, so we were to look upon to the pH of this concentration of H positive indicating the acidic pH, that is in the option C we are having. So this is how you can find the acidic medium. So generally the pH meter it is from 0 to 14 we say it, that is at the room temperature, which is at 25 degrees centigrade. But here if you see temperature they have changed it. It is 100 degrees centigrade now. So Kw value it has also increased, right? So Kw has increased. So based upon that, your pH of the pH meter it is gonna vary. Now pH meter will be 0 to pKw value, which is 12.126. That after solving this Kw value we are getting. Okay, so this is how the station was to be solved. Next is we have this question. It says that what will be the pH of a solution produced by adding 20 ml of 1 molar HCl to 1 liter of a solution containing the acetic acid and the sodium acetate. So we are having now the acetic acid, how much amount it is there? That is 1 liter and zero point 0.1 molar we have added it. So zero point 0.1 molar. So these many millimoles we will be getting, that is 0.1 moles of it we will be having it. The sodium acetate we are having is CH3COO negative and the Na positive. Its amount it is 1 liter and the zero point 0.1. So that means it is also your 0.1 mole of it you are having. Now the HCl that you have added, it is gonna be 0.02 moles. Right. Now, in the solution, you will be having the sodium acetate that can react with this HCl. So, sodium acetate that we are having, this can be reacted with the HCl, that because these solutions you were having, that is acetic acid and sodium acetate, and on that you are adding the HCl you are adding it. Okay. So this HCl it can show the reaction with your sodium acetate, which is gonna give you the formation of acetic acid, and along with that the NaCl it will be formed. How much of this it will be formed? So you are having the HCl as 0.02 moles of it, and sodium acetate it was your zero point 0.1 mole. So this is your limiting reagent. So based upon that, the acetic acid amount formed is your 0.02 over here, right? That means the acetate amount that we will be having is 0.1 minus of this limiting reagent that has reacted, which is your 0.02. We will be left is with 0.02 moles of it. Whereas the acetic acid, the final concentration that you will be seeing it, that was initially zero point 0.1 we were having it, and 0.02 of it has been formed on addition of the HCl. That means we will be having it as 0.12 moles of it. That means solution is still your acidic buffer only, just the concentration of the salt and the acid it has changed now. Okay, so now we can just find the pH, that is for the acidic buffer we know It is pH is equal to the pKa plus of the log of salt upon the acid concentration. Alright, so pKa value we have as 4.76 plus of the log of salt concentration it is 0.08 and acid is 0.12. So this is gonna be 2 by 3 we will be having. So 4.76 plus of the log of 2 minus of the log of 3 it will be there, which will be 4.76 plus 0.3010 minus of the 0.477. So solving this, the value will be 4.584. Okay, so this is gonna be the pH 4.58 that is in the option A we are having it. So this is how this question was to be solved. That is with the addition of the HCl, the species are remaining the same, their just amount it has changed. Right? Now the next question we have is this one. A basic buffer is solution is formed by mixing of a weak base plus the salt of the weak base with the with strong acid. So this is the basic buffer that is weak base and its salt that is in the option A that is given to us. Next we have is this. In the quantitative volumetric analysis for the ideometric determination of the copper, what will be the required amount of the copper sulfate dot 5 water for preparing 100 ml of N by 40 standard solution? Reactions involved are this. Okay. So normality we know it is N by 40, that is equal to the number of the gram equivalents of the solute, gram equivalents of the solute upon the volume of the solution in the liters. Volume of the solution in the liters. Right. Now this gram equivalents, number of gram equivalents is given weight upon the equivalent weight into the volume as it is it will be remaining. Right. So this one, just substitute these values and you will be getting the given weight value as. So we are having now it is N by 40, which means 1 by 40. Now the volume of the solution it is given us to be 100 ml, that you can take it into the liters. This will give you the number of gram equivalents, which is given weight upon the equivalent weight. Now the equivalent weight it is molecular weight. This is your equivalent weight. Now the given weight we can find it out as 1 by 40 into the multiplying this factors, that is 100 into 10 raised to the power of minus of 3. Equivalent weight is molecular weight upon the n factor. Equivalent weight is molecular weight upon the n factor. Now for the copper sulfate equivalent weight, this molecular weight it is given, which is 159.60. Now to look upon to the n factor, you see copper 2 positive, it is going to be copper in the plus 1 oxidation state. So that means from the plus 2 it is going to be plus 1. So n factor it is gonna be equal to the 1 only. So this will, solving this will give you the given weight. Okay, so solving this, the value you will be getting it as 0.39 grams. That is gonna be the amount of the solute which is required to prepare your this N by 40 standard solution. So this is the weight that we require. So the answer becomes the option C in this case. Right? Next is this one. It says consider the following characteristics of a primary standard. So a substance which is usually of the higher molecular weight, this we know. It is 100% pure with less purity of only 0.01 to 0.02%. Okay. The substance is stable indefinitely at the room temperatures. This statement is also the true one. These are some of the characteristics which are given. Okay, so based upon these characteristics, we have to find it out which one of the given pairs is satisfying these statements. So this is statement is we already know that with the change in the temperature or with the due course of time, the concentration of the primary standards they do not change. Right? The substance is involved in a reaction for which the equilibrium is far right to obtain a very sharp endpoint. This is also your characteristic of your primary standards. Right now, from the given pairs, if you see satisfying all the conditions, the first one, if you see any which you are having, which is your hygroscopic in the nature, that means its concentration it is gonna change with the due course of time. So this can't be used as your primary standard. Right. Next, in the option D also, if you the sulfuric acid that you are having, sulfur in it can get oxidized. So this again, it can't be used as the primary standards. Among the given options, that is for the in this oxalate, it is there in both of them. Among the KMNO4 and the K2Cr2O7, KMNO4 to some extent it can get converted to the MnO2 if not acidic medium is not provided. So in that case, this can't be also used as the primary standards. So the correct answer will be the option C in this case, where you are having the potassium dichromate and you are having this oxalate solution. Okay. Some of the more examples of the primary standards you can write it, which is your sodium carbonate, next sodium oxalate C2O4, next sodium borate or the borax Na2B4O7, this potassium dichromate K2Cr2O7, next we have is KBRO3. Next, KiO3 you can have it, or you can have the arsenic oxide As2O3. Next is KHIO3 twice. These are some of the examples of the primary standards that you can remember it. Direct questions are being asked from the primary standards that which of the following is your primary standard. So this is the primary standard examples. For the secondary solutions also you can write a few of them. For the secondary standard solutions, examples are your NaOH, you have the H2SO4 and the AgNO3. So these are few of the examples for your secondary solutions. Okay. Next one is this question you are having. It says in order to determine the amount of the calcium ion using the complexometric titrations with the EDTA using the erythrome black tea, which one of the following may be adapted to obtain a sharp endpoint? So for the determination of the calcium ions, so what we generally do is that we add a small amount of the magnesium firstly to determine the calcium ions. What it means, suppose you are having a water, that is your hard water you are having, in that you want to determine the calcium ion concentration. So for that you will be adding a small amount of the free magnesium ions, that is the option B. Why we are doing so is that because calcium it does not form a stable complex with the erythrome black tea, that is the indicator which we are using. So firstly what we do is we add the magnesium ion to it, which gives it a red wine color. So calcium it does not form a stable complex with the indicator. Okay, so what we do is we add a small amount of the magnesium ions, which on treatment with the indicator, it is gonna give you a red wine color. It will give you the red wine color. Now, EDTA when we are adding from the top, that is from the burette when we will be adding, it will be firstly reacting with the calcium ions and then with the free magnesium. At the end, EDTA it is gonna form a complex with the magnesium that is gonna be removed from this magnesium indicator complex which will be formed, and that you will be getting to know that your reaction it has completed, that your blue color complex you blue coloration you will be getting it. Blue color is obtained. This is gonna be the end point. So in order to obtain a sharp point for the calcium determination, a small amount of magnesium we are adding in it, and that is depicted by these colors. Okay, so B is gonna be the correct answer in this. Next we have is this question. It says consider an acid-base indicator as a weak acid which is showing the dissociation like this. It exhibits red color in the non-ionized form and it is exhibiting the blue color in the ionized form when we are having it. So what is the general transition range in terms of the pH units between the colors of the indicator according to the equation pH is equal to pKin plus of log of indicator upon the Hin, provided that your eyes disconcern one color only when it is 10 times as intense the other ones, which means your eyes will be able to depict the color in the acidic or in the basic medium when one of the concentration it is 10 times that of the other one. So it is given to us that 10 times intense of the other we need it. 10 times intense of the other. This is the necessary condition. So what it is representing that either this concentration of the indicator upon the HIN is 1 by 10th at the one end of the transition, at one end of the transition, one end of the transition, and the same ratio it is 10 times at the other end, at the other end. So this thing it is happening. So what it means to say, if you have this ratio which is your 1 by 10, suppose the ratio you are having, at that point from the equation that is given to us, pH is equal to the pKin plus of the log of indicator to the HIN concentration ratio is 1 by 10 we will be having, which means it is equal to the pH will be, this implies pH will be equal to the pKin minus of the log of 10, right? This I have taken in the numerator. So that becomes equal to the pKin minus of the 1 we will be having it, right? Whereas on the other hand, if you take the other end ratio, that is, if you have the ratio equal to the 10, in that case, pH will be equal to the pKin plus of the log of this concentration ratio, that is 10 if we have it. So that means pH will be equal to the pKin plus of the 1. So if you want to find the range of it, if you want to find the range, so we can label this pH1 and pH2. Suppose this is the pH1 we are having and this is the pH2 you are having. So range will be subtraction of these two, pH2 minus of the pH1. pH2 we have got it as pKin plus of the 1 and pH1 it was pKin minus of the 1. Right? So solving this pKin and pKin will get cancelled out. Range will be equal to the 2. So this is how the range you can calculate. That means the correct answer will be the option B in this case. Okay, so this range only you were to find it out. That is what is the general transition range in terms of the pH units you will be getting between the colors of the indicators. This condition it was necessary that 10 times of the intense as that of the other, which is representing this ratios which is shown over here. Okay, so these are the correct answer in this case. So this was the last question of your chapter, that was your analytical chemistry. I hope all the questions that we have discussed so far are clear to you. So if you still have doubt at any of the questions that we have discussed so far, you can ask me in the comment section. I'll surely reply to that. So that is it with your this part now. Now we are done with the organic chemistry portion, the physical chemistry as well as the analytical chemistry portion. So I hope all of this is clear. Now a few of the chapters, two, three chapters you have it, that is chemical bonding you have, or the and the periodicity, and along with that the coordination and acid base it is there, mixed match questions are there. So that we will be concluding be it together in the inorganic chemistry or chapter wise. You can let me know how you want to proceed, that we will be discussing in that same manner. Okay, so if you have not subscribed to the channel so far, so make sure you subscribe to the channel as well, because each and every question of your this UPSC Geoscientist Prelims exams we have been discussing, and much more is coming in the series. So make sure you subscribe to the channel so that you don't miss an update, and do hit the like button also for the video if you have understood the concepts, and do share it with your friends as well. So thank you so much for watching. I'll be meeting you in the next video with some new topic. Okay.